Take a deep breath and let the weight of your day settle into the soft, supporting surface beneath you. As you exhale, feel your focus drift away from the busyness of the world and toward the cool, crisp air of a changing season. There is a specific moment every year when the air shifts, losing the humid weight of summer and taking on a sharp, clean clarity. This transition is governed by the tilt of the Earth, exactly 23.5 degrees on its axis, which at this very moment is beginning to lean the northern hemisphere away from the sun's direct embrace. Within the first few days of this shift, as we cross the autumnal equinox, the sun sits directly above the equator, making day and night nearly equal in length. This is the trigger for one of nature's most spectacular chemical transformations. You might feel the change on your skin as a drop in barometric pressure, but the trees have been preparing for this for weeks. As you sit by an imaginary window, watching the first few leaves skitter across the pavement, you are witnessing the result of a biological shutdown. During the summer, leaves are green because of chlorophyll, the pigment that absorbs sunlight to create energy. But as the photoperiod, the duration of daily light, shortens, the tree realizes it can no longer sustain the high energy costs of photosynthesis. The tree begins to build what is known as an abscission layer. This is a specialized zone of cork-like cells that grows at the base of the leaf stem, or petiole. Think of it as a slow, gentle closing of a door. This layer gradually cuts off the flow of nutrients and water between the leaf and the branch. As the chlorophyll breaks down and fades away, colors that were present in the leaf all along finally become visible. The brilliant yellows and glowing oranges you see are caused by carotenoids and xanthophylls. These are the same pigments that give carrots their orange hue and corn its yellow tint. They have been there since the leaf first unfurled in the spring, masked by the dominant green of the chlorophyll. When you see a forest of bright yellow aspens or birches, you are seeing the true color of the leaf that the summer sun had hidden. Listen to the sound outside the glass. It is a dry, rhythmic rustle, a sound known as psithrism. This sound is unique to the autumn months because of the physical changes in the leaf's cellular structure. As the abscission layer completes its work, the leaf begins to lose its water content, which typically makes up about 70 to 80% of its weight during the summer. As the water evaporates, the cell walls, made of sturdy cellulose and lignin, become brittle and stiff. When the wind moves through the canopy, these hardened, desiccated leaves strike one another, creating that papery, metallic shiver that we associate with October evenings. There is a specific temperature range required for the most vivid displays. The most brilliant reds and purples are caused by anthocyanins, pigments that are not present in the leaf during the summer but are actually manufactured in the fall. For a tree to produce these deep crimsons, it needs a specific weather pattern, a succession of warm, sunny days, followed by crisp, cool nights where the temperature drops below 45 degrees Fahrenheit, or 7 degrees Celsius, but stays above the freezing point. The sunlight promotes the production of sugars in the leaf, but the cool nights cause the veins to constrict, trapping those sugars inside. In response to the high sugar concentration and the stress of the cold, the leaf produces anthocyanins as a form of sunblock, protecting the dying tissue so the tree can finish absorbing every last nutrient. You might notice that the light itself looks different this time of year. It feels heavier, more golden, as it spills across your floor. This is because the sun is lower on the horizon. The sunlight must travel through up to 10 times more of the Earth's atmosphere than it does at midday in the summer. This phenomenon, known as Rayleigh scattering, filters out the shorter blue wavelengths of light, leaving only the longer reds and oranges to reach your eyes. This is why the golden hour seems to last so much longer in the autumn, casting a long amber glow over the landscape that makes everything feel still and timeless. As the leaves finally lose their grip and tumble to the ground, they begin a new scientific journey. A single mature oak tree can shed upwards of 200,000 leaves in a single season. As they pile up on the forest floor, they create a leaf litter layer that acts as a natural insulation for the soil. This layer can keep the ground several degrees warmer than the air temperature, protecting the root systems of plants and the burrows of hibernating insects. Within these piles, a microscopic city begins to stir. The scent you often associate with autumn, that earthy, musky aroma, is caused by the release of geosmin. This is a chemical compound produced by actinobacteria in the soil as they begin to break down the fallen organic matter. When the humidity rises or a light rain falls, these spores are kicked into the air, creating the fragrance of the season. The temperature outside is falling now, perhaps hovering around 50 degrees Fahrenheit. You can feel the coolness radiating from the window pane. In the meteorology of autumn, we often see the arrival of high-pressure systems from the north. These systems bring descending air, which suppresses cloud formation and leads to those bluebird days where the sky is a deep, piercing cerulean. Because the air is sinking, it is also incredibly dry. In many temperate regions, the relative humidity in autumn can drop from a summer average of 80% down to 30 or 40%. This dryness is what allows the fallen leaves to stay crisp. If you were to step outside and walk through them, the crunch you hear is the sound of the dry cell walls fracturing. Research has shown that the sound of crunching leaves typically registers at a frequency that humans find naturally grounding and rhythmic, a sensory anchor that connects us to the cycle of the earth. Even the wind feels different. During the summer, breezes are often convective, caused by the sun heating the ground. But autumn winds are cyclonic, driven by the increasing temperature contrast between the cooling poles and the still warm equator. These winds carry the scent of wood smoke and distant rain. When the wind speed reaches about 15 to 20 miles per hour, a 4 or 5 on the Beaufort scale, the mechanical stress on the weakened petioles becomes too much, and the leaf fall reaches its peak. It is a calculated surrender. If the trees kept their leaves, the surface area would catch too much snow in the winter, and the weight would snap the branches. By shedding them, the tree becomes a streamlined skeleton, ready to withstand the coming gales. Consider the complexity of a single maple leaf lying on the grass. Its edges are curled, a process called hygroscopic deformation. As the leaf dries out unevenly with the veins holding onto moisture longer than the thin tissue between them, the leaf twists and curls into a unique three-dimensional shape. This curling creates air pockets within a pile of leaves, which further increases its insulation value. A thick layer of leaves can reduce the depth of frost in the soil by several inches, protecting the delicate mycelium networks, the fungal internet of the forest that dwell just beneath the surface. As you breathe in the cool air, imagine the billions of trees across the planet performing this same ritual. While we see it here in the brilliant maples of North America or the golden larches of the European Alps, this rhythm is a global heartbeat. In the southern hemisphere, this same process occurs in April and May. In every corner of the temperate world, the leaf area index, a measurement of how much leaf surface area covers the ground, is plummeting. This reduction in foliage actually changes the way sound travels. Without the millions of soft, flat surfaces of green leaves to absorb sound waves, the world becomes acoustically sharper. Sounds travel further. You might hear a distant train whistle or a dog barking from miles away, sounds that would have been muffled by the lush canopy of July. The air continues to cool as evening deepens. The dew point is dropping. If the temperature of the grass falls to 32 degrees Fahrenheit, the water vapor in the air will skip the liquid stage and turn directly into ice crystals, a process called sublimation in reverse, or deposition. This creates hoarfrost, which coats the edges of the fallen leaves in a delicate crystalline lace. Each crystal is a six-sided structure, reflecting the molecular geometry of water. There is a profound peace in this preparation. The trees are not dying, they are entering a state of dormancy, a deep biological sleep. They have pulled their chlorophyll back into their trunks, storing the nitrogen and phosphorus in their roots for next year. They are hunkering down, conserving energy, and simplifying their existence. As you watch the last light of the sun disappear, leaving a streak of violet and indigo across the sky, feel yourself mirroring this natural pull toward rest. The world is slowing down, the chemistry is settling, and the frantic growth of summer is giving way to the quiet, structured wisdom of the cold. The rustling leaves are a lullaby, a reminder that there is a time for letting go, a time for shedding what is no longer needed, and a time for the quiet, restorative dark. The temperature in your room is perfect, a cozy contrast to the crisp 4-5 degree air outside. The sound of the wind through the drying branches is a steady, white noise, a natural static that clears the mind. You are safe, warm, and surrounded by the steady, predictable laws of the universe. The tilt of the earth, the chemistry of the leaf, and the cooling of the atmosphere are all working in harmony, guiding the world, and you, toward a season of deep and necessary slumber. As you watch the amber light stretch across the room, it's worth considering how our ancestors interpreted this very same scene. Long before we had satellite imagery or a molecular understanding of plant biology, humans were keen observers of the turning. In ancient China, the traditional calendar was divided into 24 solar terms, which were further refined into 72 pentads, or micro-seasons lasting 5 days each. Around the 23rd of September, they recognized a period known as Shufen, or the autumn equinox. They didn't just see leaves falling, they observed the thunder losing its voice, and insects beginning to wall up their burrows. They understood that the rustle in the trees was a countdown, a biological clock ticking toward the stillness of winter. What's happening now in the forest is a form of exquisite, calculated withdrawal. Think of the tree as a vast, living library. During the summer, it keeps its most valuable volumes, the nutrients like nitrogen and phosphorus, out on the shelves of the leaves where they can be used to process sunlight. But as the temperature drops and the photoperiod shrinks, the tree must move these treasures into a secure vault within the trunk and roots. If the tree were to lose its leaves while they were still full of these elements, it would be a catastrophic waste of resources. In the 1700s, a naturalist named Robert Marsham began recording the indications of spring and the first signs of autumn on his estate in England. His records, which started in 1736 and were continued by his family for over 200 years, provide some of the earliest scientific data on phenology, the study of periodic biological phenomena. Marsham noticed that the exact date of leaf fall could vary by as much as 3 weeks depending on the year's specific weather patterns. Scientists today use his historical data to track how our climate has shifted, noting that the growing season in many parts of the northern hemisphere has expanded by nearly 11 days since the pre-industrial era. Notice how the air feels thinner tonight, almost sharper against your skin. This isn't just a trick of the mind. As the temperature of the air decreases, its capacity to hold water vapor also diminishes. For every 1 degree Celsius drop in temperature, the air's water-holding capacity decreases by about 7%. This leads to a higher vapor pressure deficit, or VPD. The VPD is the difference between the amount of moisture the air can hold and how much it actually contains. In the autumn, this deficit often grows, which accelerates the drying process of the fallen leaves. This is why a leaf that falls on a crisp 50 Fahrenheit day feels much more brittle and papery than one that falls during a humid summer storm. Deep within the branch, at the point where the leaf meets the wood, a substance called suberin is being deposited. Suberin is a complex, waxy polyester that acts as a waterproof sealant. While we've known about the abscission zone for centuries, it wasn't until the advancement of electron microscopy that we could truly see the suberin scab forming. This seal is vital. It prevents the tree's internal fluids from evaporating and protects it from fungal infections that might try to enter through the open wound left by a fallen leaf. It's a perfect architectural closure, ensuring the tree remains a closed, pressurized system during its winter dormancy. Consider the physics of the crunch beneath a footstep or a heavy gust of wind. This sound is the result of the cellular breakdown of lignin. Lignin is an organic polymer that provides structural support to the cell walls of plants. It's what makes wood woody. In a green leaf, the lignin is cushioned by water-filled vacuoles, which provide turgor pressure, the internal force that keeps a leaf flat and flexible. When the water is withdrawn and the leaf dries, the lignin becomes a rigid, crystalline structure. When that structure is stressed, it doesn't bend, it shatters. This high-frequency snap is a signal of the leaf's transition from a living organ to a component of the forest floor's O-horizon, or organic soil layer. In the 18th century, the Dutch biologist Jan Ingenhouses discovered that plants breathe differently in the light than they do in the dark, laying the groundwork for our understanding of the carbon cycle. In the autumn, we can actually measure a global hiccup in carbon dioxide levels. Because there are significantly more deciduous forests in the northern hemisphere than in the southern, the massive leaf drop in October and November causes a measurable spike in atmospheric CO2. The lungs of the planet are essentially exhaling and holding their breath until the following spring. In Japan, the practice of momi-jigari, or maple leaf hunting, has been a cultural cornerstone since the Heian period, over 1,000 years ago. They recognized early on that different species turn at different rates. For instance, the Acer palmatum, the Japanese maple, produces particularly high levels of anthocyanins, the pigments that create deep purples and reds. But have you ever wondered why some leaves, particularly on oak and beech trees, turn brown but refuse to fall? This phenomenon is called marcescence. While most trees complete their abscission layer by late October, marcescent trees keep their dead leaves all through the winter. Scientists believe this might be an evolutionary tactic. By keeping their dry, brittle leaves until the spring, these trees might be protecting their tender new buds from being eaten by deer. The dry leaves are unpalatable and noisy, alerting the tree to the presence of a browser. Furthermore, when these leaves finally drop in the spring, they provide a fresh mulch of nutrients exactly when the tree needs it most for new growth. It's a delayed gift from the previous season. As you sit by your window, you might notice the way the wind moves differently through the trees now. In the summer, a full canopy of leaves acts as a drag on the wind, creating a low-frequency hum. But as the leaves thin out, the wind interacts with the fine twigs and branches, creating an aeolian sound named after Aeolus, the Greek god of wind. This sound occurs when wind passes over a thin object, creating tiny vortices of air that alternate from side to side. The frequency of the sound is directly proportional to the wind speed and inversely proportional to the diameter of the branch. The whistle of a winter woods is literally the sound of the air being sliced by billions of tiny wooden fingers. There's a specific atmospheric condition often found on these autumn nights known as a thermal inversion. Typically, the air gets cooler as you go higher in the atmosphere. However, on a clear, calm autumn night, the ground radiates its heat back into space very quickly, a process called radiational cooling. This leaves a pocket of cold, dense air trapped near the surface, with a layer of warmer air sitting right on top of it. This inversion layer acts like a lid, trapping the scents of the forest, the smoke from distant chimneys, and the damp smell of decaying leaves close to the ground. This is why the world smells so much more atmospheric and rich during an autumn evening walk. If you were to look at a cross-section of a tree trunk during this time, you would see the formation of the latewood. This is the part of the annual growth ring that is darker and more dense. Because the tree is growing more slowly now, the cells it produces are smaller with thicker walls. This provides the structural integrity needed to survive the heavy loads of winter ice and snow. This slowing of the metabolic rate is governed by a hormone called abscisic acid. This chemical messenger travels through the tree's vascular system, telling the cells to stop dividing and start preparing for the cold. It's a biological quiet down order that affects every cell from the deepest root to the highest bud. Even the soil is changing its chemistry. As the leaves fall, they bring with them a pulse of carbon and minerals. The temperature of the soil stays more stable than the air because of its high thermal mass. While the air might be 40 degrees Fahrenheit, the soil 6 inches down might still be a comfortable 55 degrees. This temperature differential allows the decomposers, the fungi and the earthworms to remain active long after the first frost. They are the invisible engineers of the season, turning the brittle, rustling waste of the trees into the rich, dark humus that will fuel the explosion of life in 6 months' time. Picture the vast forests of the Siberian taiga or the Canadian boreal. In these regions, the transition is even more rapid. The larch tree, or larix, is one of the few conifers that is actually deciduous. It turns a brilliant neon gold before dropping all its needles. This is a rare adaptation to extreme cold, allowing the tree to survive temperatures that can plummet to -60 degrees Fahrenheit. By shedding its needles, it avoids the winter burn that occurs when the sun comes out but the ground is still frozen, preventing the tree from replacing the water it loses through its needles. There is a profound sense of intelligence in this seasonal retreat. We often think of the falling leaf as an ending, but in the context of the tree's life, it is a masterpiece of efficiency. It is the tree's way of breathing out, of simplifying its needs so it can endure. As you listen to the rhythmic scratching of a branch against the house, or the distant scuttle of a leaf across the porch, let your own internal abscisic acid take hold. Let your thoughts simplify. Let the thermal inversion of your own space trap only the warmth and the comfort of the present moment. The science of the season tells us that rest isn't just a break from life, it is a vital, active process of preparation. Like the suberin sealing the branch, let the quiet of the night seal away the stresses of the day, leaving you safe, insulated, and ready for a deep, restorative stillness. Think of the tree outside your window not as a static object, but as a complex, biological machine that has spent the last 6 months running at full throttle. During the height of summer, a single mature silver maple can move as much as 60 gallons of water every hour from its roots to its highest leaves through a process called transpiration. What's happening now is that the tree is effectively winterizing its internal plumbing. This movement of water is driven by something scientists call the tension-cohesion theory. Imagine a microscopic straw stretching from the soil all the way up 100 feet into the air. Water molecules are sticky, they cling to one another through hydrogen bonds. As water evaporates from the leaf's surface, it pulls the entire column of water upward. But as the autumn air cools to an average of 50 degrees Fahrenheit, the tree begins to intentionally break that tension, allowing the column to rest, so the liquid won't freeze and shatter the delicate xylem vessels inside the trunk. Notice the intricate pattern of the veins on a leaf that has landed on your windowsill. If you look closely, you'll see a network that looks remarkably like a map of a bustling city. This is the venation of the leaf. Just as a city has major highways, secondary roads, and tiny alleys, the leaf has a primary midrib, secondary veins, and a vast web of tertiary capillaries. These veins do more than just transport water. They provide the structural rebar that holds the leaf's flat concrete surface, the lamina, out toward the sun. In the summer, these cells are plump and rigid with water, a state known as high turgor pressure. This pressure can be as high as 5 to 10 atmospheres, comparable to the pressure inside a professional racing bicycle tire. As the leaf prepares to drop, it purposefully drains this pressure. What you are left with is the skeletal remains of that hydraulic system, which is why the leaves begin to curl and twist into those familiar organic shapes. At this very moment, the air around those fallen leaves is undergoing a transformation in density. Cold air is significantly heavier and more viscous than warm air. When the temperature sits at a crisp 40 degrees Fahrenheit, the air molecules are packed closer together than they were during a 90-degree July afternoon. This change in density alters the way sound waves travel. While a summer forest might feel muffled because the humid, less dense air scatters sound, the cold, dry air of autumn acts like a high-fidelity speaker. This is why the rustle of a leaf, a sound that typically registers at about 20 to 30 decibels, seems so much more distinct and crisp in October. For comparison, 20 decibels is the same intensity as a human whisper or the hum of a quiet library. The sound is sharp because the dry, brittle edges of the leaf are vibrating against a medium that is literally tighter and more efficient at carrying those vibrations to your ear. Consider the leaf pile on the ground as a form of natural fiberglass insulation. Just as you might put an extra blanket on your bed or check the insulation in your attic, the forest is laying down its own protective barrier. Scientists have measured the R value, the measure of thermal resistance of leaf litter. A thick, 6-inch layer of dry, loosely packed leaves can have an insulation value similar to a thin layer of modern home insulation. Because the leaves are curled, they create millions of tiny dead air pockets. Since air is a poor conductor of heat, these pockets trap the warmth of the earth. Even when the air temperature dips toward the freezing point of 32 degrees Fahrenheit, the soil beneath a healthy layer of leaves might remain a steady 45 or 50 degrees, providing a safe haven for the macrofauna of the soil, such as beetles and earthworms, who are slowly retreating into a state of diapause. What's happening now is a global phenomenon. though it looks different depending on where you stand on the planet. In the southern hemisphere, specifically in the alpine regions of Tasmania, there is a species called the Nothofagus gunnii, or the tanglefoot. It is Australia's only cold climate deciduous tree. While we watch the leaves turn in October, the tanglefoot performs this same golden transformation in late April and May. Even in the tropical rainforests, there is a version of this rustling. While these trees don't drop all their leaves at once, they follow a leaf exchange pattern. A tropical tree might shed 10% of its canopy every month, ensuring the forest floor is always covered in a thin, crackling carpet of organic matter. This global rhythm is a constant exhale of carbon, a process that has been occurring for over 350 million years since the first Devonian forests appeared on the Earth's surface. Picture the surface of a leaf through a microscope. You would see thousands of tiny, mouth-like openings called stomata. There can be as many as 1,000 stomata on a single square millimeter of a leaf's underside. These are the windows of the tree, opening to let in carbon dioxide and closing to keep in moisture. During the summer, these windows are constantly adjusting based on the sun's intensity. But as the autumn chill sets in, the tree produces a hormone called abscisic acid, which acts like a biological deadbolt, locking these stomata shut for the final time. This prevents the leaf from losing any more water through evapotranspiration, which is the plant version of sweating. By locking the windows, the tree ensures that its remaining internal moisture stays locked within the trunk and branches, protected from the drying winds of the coming winter. Scientists discovered that the scent of autumn, that specific earthy aroma that fills the air after a light rain or a heavy gust of wind, is partly due to the release of terpenes. Terpenes are organic compounds found in the resins of many trees. As the leaves begin to dry and their cellular structures break down, these oils are released into the atmosphere. When the temperature is between 45 and 55 degrees, these heavy molecules don't rise and dissipate quickly. Instead, they linger near the ground. This is the same principle as a perfume smelling stronger on your skin than it does in the bottle. The warmth of the decaying leaf pile provides just enough energy to volatilize these oils, creating a natural aromatherapy session that signals to our brains that the environment is shifting toward a period of rest. The color of the light you see hitting the trees is also influenced by Mie scattering. While the blue sky of summer is caused by smaller molecules scattering blue light, the hazy, golden quality of autumn light is often caused by larger particles in the air like dust, pollen, and those very same terpenes being released by the trees. These larger particles scatter all wavelengths of light more equally, which can make the sun look larger and softer on the horizon. This soft light is a visual cue that matches the physical sensation of the season, a rounding of the edges, a softening of the world's harsh summer lines. Notice how the tree is not simply losing its leaves, but is actively pushing them away. The process of abscission is so precise that the scar left behind is perfectly waterproof within hours. This is an incredible feat of biological engineering. If you've ever used a tear-away strip on a package, you've experienced a primitive version of this. The tree grows a layer of cells that are physically weaker than the ones around them, but chemically tougher due to the addition of lignin and suberin. This ensures that when the wind reaches a specific force, often around 12 to 15 knots, the leaf detaches cleanly without tearing the living tissue of the branch. It is a graceful exit, a planned departure that ensures the tree's survival. Deep within the forest floor, the energy from the summer sun is being recycled. The leaves that were once 90 feet in the air, capturing photons and turning them into sugar, are now being dismantled by detritivores. An earthworm can process its own body weight in organic matter every single day. As they consume the fallen leaves, they are essentially digesting the previous season, turning the captured sunlight of July into the nutrient-rich soil of next April. This is the circular economy of the natural world. Nothing is ever truly lost, it is simply changing its state of matter, moving from a high-energy vertical existence to a slow horizontal and grounded one. As you listen to the rhythmic, papery scuttle of the wind through the garden, imagine the trees as dormant batteries. They have spent all year charging up, and now they are entering a low power mode, much like a laptop that has been closed but not completely turned off. their metabolic rate will drop by as much as 90%. Their heartbeat, the slow pulse of sap, will become almost undetectable. They are waiting, and in this waiting there is a profound sense of security. The tree knows exactly how much energy it has stored. It knows the exact chemical composition of its protective bark. It is not afraid of the coming cold because it has spent the entire turning preparing for it. The temperature in your room might be a steady 68 degrees, but your mind can sense the 40-degree world outside. This contrast is one of the most comforting aspects of the season. The concept of thermal delight is a term used by architects to describe the pleasure we feel when moving between different temperature zones. The chill of the autumn air makes the warmth of your blanket feel more active. It gives the warmth a purpose. Just as the tree finds safety in its dormancy, you can find a deep biological satisfaction in the simple act of being warm and still while the world outside performs its grand scientific retreat. The rustling leaves are the soundtrack to this preparation, a dry, rhythmic reminder that everything in nature has a time to shine, a time to fall, and a time to rest deeply in the quiet, insulating dark. Observe the way the shadows in your room have grown longer and more lean. This is a direct consequence of the sun's decreasing solar altitude. In the height of summer, the sun might reach an angle of 70 degrees above the horizon, but as we move through October, that angle drops significantly, often down to 30 or 40 degrees at noon in temperate latitudes. This low-slung sun creates a unique lighting effect called backlighting, which illuminates the translucent cells of the autumn leaves from behind, making a maple tree appear as if it is glowing from within. It is a biological stained glass window, powered by the final, slanted rays of the season. What's happening now is that the entire hemisphere is participating in a wave of color that migrates across the map. Scientists have tracked this progression and found that the peak of the autumn foliage generally moves southward at a rate of approximately 15 to 25 miles per day. In the mountains, this change descends vertically as well, dropping about 100 feet in elevation every day. This means that if you were to stand on a peak in the Blue Ridge Mountains or the Scottish Highlands, you could literally watch the season sink into the valleys over the course of a week. It's a slow-motion cascade of gold and crimson, governed by the cooling of the Earth's surface and the shifting position of the jet stream. Consider the Indian summer phenomenon that often occurs during this period. You might notice a sudden, unexpected return of warmth, where the temperature climbs back above 70 degrees Fahrenheit or 21 degrees Celsius after the first killing frost has already passed. This isn't just a random occurrence. It is caused by a massive, stagnant, high-pressure system, sometimes called an anticyclone, stalling over the region. The air within this system sinks and warms through a process known as adiabatic compression. This stagnant air traps the dust and the scents of the harvest, creating that hazy, nostalgic atmosphere we associate with late October. It's a brief, warm exhale from the atmosphere, providing a final window for the trees to finish their nutrient recovery. Deep within the tree's vascular system, a process called resorption is reaching its peak. This is one of nature's most efficient recycling programs. Before the leaf detaches, the tree breaks down the complex proteins and pigments within the leaf into their basic components, primarily nitrogen and phosphorus. These vital elements are then pumped back through the phloem, the tree's inner nutrient highway, and stored in the woody tissues of the trunk and roots. Research has shown that deciduous trees can recover as much as 50% of the nitrogen from their leaves before they fall. This is an active, metabolic process that requires energy. The tree isn't just letting go. It is carefully packing its bags for the long winter journey ahead. What you are witnessing is a masterpiece of long-term planning. This seasonal shift is a mirror to the way we manage our own energy. Just as a tree cannot remain in a state of high-growth production forever, our own lives require these periods of resorption moments where we pull our focus inward, recover our resources, and shed the external foliage that is no longer serving us. Think of this season as the Earth's attic, a time of tidying up and storing away the treasures of the year so they aren't lost to the coming cold. Picture the way the dew forms on the fallen leaves in the early morning. This is governed by the dew point, the temperature at which the air becomes 100% saturated with water vapor and can no longer hold it in gaseous form. In the autumn, as the ground loses heat rapidly through infrared radiation, the surface of the leaves can cool down much faster than the surrounding air. If the leaf temperature falls below the dew point, water molecules begin to condense on the surface. If that temperature further drops below 32 degrees Fahrenheit, you get the white frost, or hoar frost, that outlines every vein and serrated edge of the leaf in silver. This process, known as deposition, turns the forest floor into a crystalline landscape, preserving the leaves in a temporary frozen sculpture. At this very moment, the wind might be picking up, a phenomenon often caused by cold frontal passages. As a mass of dense, cold Canadian or Arctic air moves in, it slides under the warmer, lighter air already in place, lifting it up and creating a drop in barometric pressure. This pressure gradient is what generates the wind that finally liberates the leaves from their branches. When you hear that papery scuttle across the pavement, you are hearing the sound of air moving from areas of high pressure to low pressure, a physical manifestation of the earth seeking equilibrium. The crinkle of the leaf itself is the vibration of the dried cellulose and lignin at frequencies typically between 500 and 2000 Hz, a range that the human ear is specifically tuned to perceive with. Great clarity. Scientists discovered that the redness of a particular autumn is often determined by the weather of the previous summer. If the summer was characterized by a slight, non-lethal drought, the trees produce more sugars in their leaves, which leads to a more intense production of anthocyanins. However, if the summer was excessively wet, the leaves may lack the sugar concentration needed for those deep crimsons, leading to a more muted yellow and brown season. Every autumn is a biochemical record of the year that preceded it. The leaves are telling the story of the July rains and the August sun, transcribed into the language of color and texture. Notice the way the fallen leaves begin to nestle into one another. This is due to their hygroscopic nature, their ability to absorb and release moisture from the air. When it's dry, the leaves curl up, creating air pockets. When it rains or the humidity rises, the leaves soften and flatten out, forming a dense, waterproof mat. This mat is essential for the pedogenesis, or soil formation, of the forest. Beneath this layer, the temperature remains remarkably stable. While the air might fluctuate by 30 degrees in a single day, the soil 4 inches down might only vary by 2 or 3 degrees. This thermal stability is what allows the mycorrhizal networks, the symbiotic fungi that connect the trees, to continue exchanging nutrients even when the world above is freezing. There is a profound personal connection to be found in this scientific reality. We often feel a sense of seasonal affective shift as the days shorten, but this is a deeply biological response. Our bodies, like the trees, are responding to the circannual rhythm. As the light levels drop below a certain threshold, our pineal glands increase the production of melatonin, the hormone that regulates sleep. We are literally being chemically signaled by the planet to slow down. The rustling outside is a call to match our internal pace with the external world. We are part of this atmospheric system, not separate from it. Imagine the leaf area index of the entire planet. During the summer, the Earth has millions of square miles of green leaf surface, creating a massive carbon sink. As these leaves fall, the Earth exhales. This global breath is so large that it can be seen in the fluctuating CO2 data from the Mauna Loa Observatory. Every October, the concentration of carbon dioxide in the atmosphere begins to rise slightly as the northern hemisphere's trees go dormant and the leaves begin to decompose. It is as if the planet itself is taking a slow, deep breath in, holding it through the winter, and preparing to exhale a fresh burst of oxygen come spring. As you settle further into your own space, think of the thermal mass of your home. Just as the soil holds the heat of the summer sun, your environment is a buffer against the cooling world. The science of the season teaches us that protection is often a matter of layers. The tree has its bark, the leaf litter has its air pockets, and the soil has its depth. You too have your layers, your blankets, your home, and the quiet, insulating thoughts of a year well spent. The sound of the wind through the drying canopy is a form of pink noise. Unlike white noise, which has equal intensity at all frequencies, pink noise has more power at lower frequencies, making it sound deeper and more natural to the human ear. It mimics the rhythm of a heartbeat or the flow of blood. This is why the sound of wind in the autumn trees is so uniquely soothing. It is a frequency that matches our own internal biological signatures. It is the sound of the world's metabolism slowing down to a restful, sustainable throb. The leaves continue to fall, each one a tiny solar panel that has completed its mission. They land with a weight of only a fraction of a gram, yet collectively they represent tons of recycled energy. They are the organic capital of the forest. As you listen to them rustle, let yourself appreciate the economy of nature, the way nothing is wasted, the way every ending is a preparation, and the way the cold is simply a different kind of intensity. You are safe in the middle of this grand chemical transition. The earth is doing the heavy lifting of storage and recycling, leaving you with nothing to do but observe, learn, and drift toward your own necessary season of rest. What is occurring now, as the evening deepens and the air continues its steady descent in temperature, is a sensory masterclass in physics and chemistry. You may notice the way the silence outside feels thicker. This isn't a romantic observation, it is a measurable acoustic change. In a summer forest, the lush, water-filled leaves act as acoustic baffles, absorbing sound waves. But in autumn, once the leaves have dried and fallen, the world's absorption coefficient changes. Without those soft surfaces, sound waves bounce more freely off the bare trunks and the hard ground. This is why you can hear the distant snap of a twig or the dry, papery rattle of a single leaf from much further away. This sound, that specific shiver in the trees, is called citharism, and it is most pronounced when the leaves reach a moisture content of less than 10%. Notice how the scent of the evening has shifted from the floral, sweet notes of summer towards something more grounded and sharp. This is the result of a chemical process involving volatile organic compounds, or VOCs. During the warmer months, trees like oaks and maples release isoprene to help them cope with heat stress. As the temperature drops below 55 degrees Fahrenheit, or about 13 degrees Celsius, isoprene production halts. What takes its place is the aroma of leaf litter decomposition. Scientists have discovered that humans are incredibly sensitive to a compound called geosmin, which is produced by soil-dwelling bacteria like Streptomyces. We can detect geosmin at concentrations as low as 5 parts per trillion, a sensitivity far greater than a shark's ability to smell blood in the ocean. When the autumn humidity rises, these tiny molecules are lofted into the air, creating that signature earthy smell that signals the season's transition. Picture the texture of a leaf you might find on the ground tomorrow morning. It's no longer the supple, waxy surface it was in July. What's happening now is the oxidation of polyphenols into tannins and phlobophene. These are the same chemicals found in tea and leather. When the brighter carotenoids and anthocyanins, the yellows and reds, eventually break down, they leave behind these sturdy brown pigments. Tannins serve a final protective purpose. They are bitter and astringent, discouraging fungi and bacteria from consuming the leaf too quickly. This allows the leaf to remain intact on the forest floor, serving as a biological shingle that protects the soil from the erosive power of late autumn rains. At this very moment, something curious is happening in the local lakes and ponds, a process known as lake turnover. It is a vital part of the autumn rhythm. Water has a singular property. It is at its heaviest and densest at exactly 39.2 degrees Fahrenheit, or 4 degrees Celsius. As the autumn air cools the surface water of a lake down to this specific temperature, that water becomes heavier than the water beneath it. It sinks to the bottom, forcing the nutrient-rich water from the depths to rise to the top. This vertical mixing recharges the entire body of water with oxygen, preparing the aquatic life for the winter months when the surface might freeze over. It is a massive, silent circulation, driven entirely by the cooling air you feel against your window. Consider the color temperature of the light hitting the trees during these shorter days. Because the sun sits lower in the sky, its light must pass through an air mass, AM coefficient, that is much higher than in the summer. At a solar altitude of 30 degrees, the sunlight travels through twice as much atmosphere as it does at 90 degrees. This extra travel time filters out the high-energy blue and violet light, leaving the landscape bathed in the long-wave spectrum of gold, amber, and red. This isn't just aesthetic, it's a physical reality of the atmosphere, acting as a giant, protective sieve. Scientists have noted that this specific quality of light, often around 2,500 to 3,000 Kelvin, triggers a reduction in cortisol in the human brain, naturally easing us into a state of evening relaxation. What's happening now within the animal kingdom is equally driven by this seasonal chemistry. Many ectotherms, or cold-blooded animals like the wood frog, are beginning to prepare for a state of cryoprotection. As the leaf litter thickens and provides insulation, these frogs produce high concentrations of glucose and glycerol in their blood. This acts as a biological antifreeze, preventing ice crystals from forming inside their cells, which would otherwise be lethal. They can actually survive having 65% of their body water frozen solid. They wait, tucked beneath the rustling leaves, their heartbeats slowing until they are almost imperceptible, perfectly synced with the dormant rhythm of the trees above them. Notice the way the wind behaves differently as the canopy thins. In the summer, the wind is laminar. It flows in smooth, predictable layers over the top of the full trees. But as the leaves drop, the wind becomes turbulent. It dives down between the branches, swirling around the trunks and scuttling the fallen leaves across the ground. This turbulence is essential for the distribution of seeds and spores. It also helps to gas exchange the soil, pulling fresh oxygen into the spaces between the fallen leaves. When you hear that sudden whoosh and the following rattle of dry foliage, you are witnessing the forest breathing in a way that is only possible during this specific window of the year. Scientists discovered that the crunch of a leaf is a result of the structural failure of lignin at a very high frequency. When you apply pressure to a dried leaf, the rigid, waterless cell walls don't deform, they fracture. This fracture creates a sound profile that peaks between 2 and 4 kHz, interestingly, the same frequency range that the human ear is most sensitive to. There is a deep evolutionary connection to this sound. For our ancestors, the rustle of leaves was the most reliable way to detect the movement of animals or other people in the woods. Today, that sound serves as a rhythmic anchor, a tactile and auditory confirmation that the year is moving toward its close. Deep within the soil, the wood wide web, the mycelial network of fungi, is experiencing a surge in activity. While the trees are shutting down their above-ground production, they are sending a final pulse of carbon-rich sugars down through their roots to their fungal partners. In exchange, the fungi are providing the trees with concentrated phosphorus and nitrogen, which the trees will store in their heartwood for the spring. This is a massive subterranean transaction involving millions of miles of microscopic threads. At this very moment, the forest floor is a busy marketplace, a silent hub of commerce that ensures every living thing has the resources it needs to survive the coming freeze. In the southern hemisphere, in the deciduous forests of southern Chile and Argentina, the Nothofagus obliqua, or the robel tree, is currently in its own season of growth. But it too will face this turning in several months. The global synchronization of these events is a testament to the Earth's precise axial tilt. Whether it's the maples of Vermont or the robel of the Andes, the biological machinery is the same. The trees are following a set of genetic instructions that are over 100 million years old, a code that tells them exactly when to build the abscission layer and when to let the chlorophyll fade. Picture the way a light rain interacts with the autumn leaves. Because the leaves are coated in a waxy cuticle that has thickened over the summer, they are initially hydrophobic. Water droplets bead up and roll off the surface, a phenomenon known as the lotus effect. This ensures that the water doesn't sit on the leaf and promote fungal rot while the leaf is still attached to the tree. Once the leaf falls and begins to break down, this wax wears away, allowing the leaf to absorb water. A dry leaf can absorb up to twice its weight in moisture, turning the brittle, noisy crunch into a soft, silent carpet. This transition from brittle to soft is a natural volume control for the forest, dampening the sound of the world as the weather turns wetter and colder. The barometric pressure is likely rising now as a cold high moves into your area. High pressure means the air is sinking, suppressing the rise of moisture and resulting in those clear, star-filled nights where the temperature can plummet 20 or 30 degrees in just a few hours. This is radiational cooling. Without a blanket of clouds to trap the heat, the Earth's surface radiates its energy directly into the cold vacuum of space. The fallen leaves act as a final shield for the ground, catching some of that heat and holding it close to the roots. It is a beautifully designed system of thermal management, where even the waste of the previous season becomes the primary protection for the next. As you grant yourself the space to be fully present in this moment, let the science of the season reassure you. The turning is not a chaotic event. It is a highly ordered, molecularly precise transition. The trees aren't losing their leaves, they are shedding them with the same intentionality that we shed the worries of our day. The rustling you hear is the sound of a living system optimizing itself for survival. It is the sound of efficiency. It is the sound of the world's metabolism finding its resting heart rate. Let your own pace match the cooling air and the sinking sun. Allow your thoughts to settle like the leaves no longer fluttering in the frantic winds of daily responsibility, but finding their place in a quiet, protective layer of rest. The chemistry of the night, the physics of the cooling air, and the biology of the dormant trees are all converging to create a sanctuary of stillness. You are a part of this rhythm, a biological entity governed by the same laws of light and temperature. And just like the forest, you have earned this season of quiet, this moment of resorption, and this transition into the deep, restorative dark. The evening has finally deepened into a profound, velvety stillness, and the trees outside have completed their most demanding work of the year. While it looks like a simple cessation of activity, what you are observing is the final stage of a highly complex, step-by-step physiological shutdown known as hardening off. This process occurs in two distinct phases. The first phase was triggered weeks ago by the shortening of the days, but the second phase is happening right now, at this very moment, as the temperature drops toward the freezing point. Scientists have discovered that as the thermometer hits that 32 degree Fahrenheit mark, the tree begins to move water out of its individual cells and into the spaces between them. This is a vital protective measure. If the water were to freeze inside the cells, the resulting ice crystals would expand and rupture the delicate cellular membranes. By keeping the intracellular fluid concentrated with sugars and proteins, a biological antifreeze, the tree can survive temperatures as low as -40 degrees Fahrenheit without its living tissue ever turning to ice. Notice how the tree's silhouette has changed. Every leaf has fallen, but if you were to look closely at the tips of the branches, you would see that the tree is already prepared for the future. Nestled at the base of every fallen leaf is a terminal bud, already formed and encased in bud scales. These scales are modified, toughened leaves that are often coated in a sticky, resinous wax. This wax serves as a microscopic waterproof seal, protecting the embryonic leaves and flowers for next spring from the desiccating winds of winter. Inside that tiny bud, which is often no larger than a grain of rice, the entire blueprint for next May's growth is already folded away in a state of endodormancy. The tree is not just waiting. It is a pressurized vessel of potential energy, held in a state of perfect, suspended animation. As the air temperature outside your window continues to slide, currently perhaps reaching a crisp 38 degrees, the atmosphere is performing a final nightly adjustment called radiational cooling. Because the sun has set, the Earth's surface is no longer receiving short-wave solar radiation. Instead, it is emitting long-wave infrared radiation back into the clear night sky. If there are no clouds to act as a thermal blanket, this heat escapes directly into the upper atmosphere. This process is incredibly efficient. A field of dry, fallen leaves has an emissivity of about 0.96, meaning it is nearly perfect at shedding its heat. This rapid cooling of the ground creates a temperature inversion, where a thin layer of cold, dense air is trapped right against the Earth, while a layer of slightly warmer air sits just a few hundred feet above it. This inversion layer has a fascinating effect on the sounds you hear as you settle into bed. Sound waves travel faster in warm air than in cold air. When a sound like the distant, rhythmic hoot of an owl or the low rumble of a far-off train travels upward and hits that warmer layer of air, it actually refracts or bends back down toward the ground. This atmospheric phenomenon acts like a natural amplifier, focusing sound waves along the surface of the Earth. This is why, on a calm autumn night, the world feels both quieter and more acoustically present. The rustle of a single leaf 3 gardens away might reach your ears with startling clarity, a gentle, papery reminder of the Earth's slow, mechanical cooling. Consider the way your own body is mirroring this environmental transition. To prepare for deep sleep, your internal thermostat, the hypothalamus, begins a step-by-step process of cooling your core temperature. Research in chronobiology shows that for high-quality rest, your core body temperature must drop by approximately 2 to 3 degrees Fahrenheit, or about 1 to 1.5 degrees Celsius. At this very moment, your body is shunting heat away from your internal organs toward your skin and extremities, which is why your hands and feet might feel slightly warmer as you drift off. This is your personal version of radiational cooling. As your temperature reaches its nightly nadir, or lowest point, your metabolic rate drops by about 15%, perfectly synchronizing your internal rhythm with the dormant pulse of the trees outside. Deep within your brain, a chemical process called sleep pressure is reaching its peak. Throughout the day, as you move and think, a molecule called adenosine builds up in your system as a byproduct of energy consumption. By the time the autumn sun sets, the concentration of adenosine is high enough to signal to your suprachiasmatic nucleus that it is time to transition. At the same time, the specific color temperature of the twilight, the absence of the 480 nanometer blue light that characterizes the midday sun, triggers the pineal gland to release melatonin. This isn't just a sleep hormone. It is a systemic signal that tells every cell in your body to begin the process of metabolic resorption, much like the tree pulling its nitrogen back from the leaves. Picture the way the fallen leaves are now interacting with the soil. Beneath that insulating layer of lignin and cellulose, a process called humification is beginning. The moisture from the evening dew, which forms when the air reaches its saturation vapor pressure, is being absorbed by the dry leaf tissue. This moisture allows the fungi to secrete enzymes like cellulase and hemicellulase, which slowly dismantle the leaf's sturdy skeleton. As the leaves break down, they release carbon to nitrogen ratios that are perfectly balanced to nourish the soil. Scientists have measured that a healthy forest floor can contain up to 5 tons of decaying organic matter per acre, all of it working to store carbon and regulate the ground's thermal inertia. The soil is a giant, slow-moving heat sink, holding onto the summer's warmth long after the air has turned bitter. Notice how the wind has died down to a mere cat's paw breeze less than 3 miles per hour. In the absence of the sun's convective heat, the atmosphere becomes stably stratified. The air molecules are no longer churning in frantic warm updrafts. They are settling into quiet, horizontal layers. This stability is the atmospheric equivalent of a deep, slow breath. The kinetic energy of the afternoon wind has dissipated, leaving only the potential energy of the cold, still night. In this stillness, the Earth's rotation continues at a steady 1,000 miles per hour at the equator, but here, in the embrace of the autumn night, the only movement is the slow, deliberate transition of water vapor into frost. As you move closer to sleep, think of the trees as your silent companions in rest. They have spent the last 6 months in a state of net primary production, creating life from light. Now, they are entering quiescence, a state where their growth is halted by the environment, which will eventually deepen into dormancy. They are conserving, they are simplifying. Their respiration rate has slowed to the bare minimum required to keep their cellular structures intact. They are proof that there is immense strength in stillness, and that the most productive thing a living system can do at this time is to stop, to wait, and to recover. Your own breathing is now finding its natural nocturnal cadence. As you inhale the cool, filtered air of your room, your heart rate is slowing, moving from its active daytime frequency toward a restful bradycardia of sleep. The delta waves in your brain are beginning to emerge slow, high-amplitude oscillations that oscillate at a frequency of 0.5 to 4 Hz. These waves are the neurological signature of deep restorative rest. This is when your brain performs its most vital maintenance, much like the forest floor recycling the fallen leaves. During this phase, the glymphatic system increases its activity by as much as 60%, effectively clearing the metabolic byproducts of the day's thoughts and actions. The rustling leaves outside have become a distant, rhythmic white noise, a frequency that blankets the world in a sense of safety. The albedo of the Earth, the amount of light it reflects, is at its most neutral now, as the vibrant colors of autumn give way to the muted, dark tones of the winter wood. The world is turning inward. The tilt of the planet is carrying you further into the shadow of the year, a place of profound, quiet, and necessary dark. You are part of a global exhale. You are part of an ancient, astronomical rhythm that has governed life for eons. Before you go, hold on to these truths of the season. Rest is a vital biological requirement, not a luxury. Like the tree, you have stored everything you need to survive the coming quiet. Your body knows exactly how to navigate the transition into the dark. Every ending in this season is the chemical foundation for a new beginning. The cold outside only serves to make the warmth within more meaningful. You are safe, you are insulated, and you are synchronized with the earth. The temperature has settled. The abscission is complete. The world is dormant, and the air is still. The thermal mass of your home and the comfort of your blankets are your horizon, your protective layer against the night. Let the slow 0-5 Hertz rhythm of the earth carry you into the deep, restorative stillness of the season. The science of the night is now the science of your sleep. The rustling has stopped. The preparation is over. It is time to let the darkness do its quiet, essential work. Good night.